Hello everyone! Hope you're having a fantastic day so far. Today we're going to be talking about something you have been dealing with for quite some time actually. This is going to be nothing new. It's going to just put a name to something you've already known how to do for a really long time. So today what we're going to be doing here is talking about polynomials. Polynomial means many terms, right? So it says a polynomial function is the sum of power functions. So you take a bunch of power functions like x to the nth power, x to the n minus 1, x to the a. So if n was 3, this would be x to the third, n minus 1 is x squared, x, and no x, right? N is the highest power, and it's called the degree of the polynomial. So if this n was a 3, if the biggest power is a 3, it's a third degree polynomial. And n has to be an integer. Now this is the important one. An integer bigger than 0. Alright? That means it's got to be a whole number bigger than 0. So determine if each of the following are polynomial functions. I'm going to try and go through these pretty quick since we already know how to do most of them. So I just need to look, is it all whole number exponents, positive exponents, bigger than 0, and figure out some stuff. And if it is, give the degree. So is the first one 3x to the fourth plus 6x squared minus 5. Whole number exponents. No negative exponents anywhere. So is it a polynomial? Yes, it is. It has a degree of 4. It's the highest exponent. And then it says give the number of terms. So this one has 1, 2, 3 terms. Remember, a term is separated by addition or subtraction. This one, remember the x squared is like saying x to the 1/2 power, right? So is this one a polynomial? No, because this is a fraction on the power. So no, the square root of x is x to the 1/2. And since this is not an integer, it says not an integer. There's a reason. They explain why not. Not an integer power is what we're talking about there. Let me put that beneath power. It's got to be a whole number. Down here, is this a polynomial? Well, remember, it's got to be greater than 0, right, for all your integers. This one's less than 0. So is it a polynomial? No. You have a negative exponent. Okay. This one. 3 over x to the 3 over x minus 5. Is it a polynomial? No, because the negative exponent down here. Now this, you may have not seen this before, but no, it is not a polynomial, and here's why. 3 over x is the same thing as 3 times x to the negative 1. If this is a 1 down here, and we make it negative, we can bring it up. Right, so again, no, this is a negative exponent. Alright, what about down here on 5? Well, here's my variable. I've got a positive 1 for an exponent, so is this a polynomial? Yes. Your degree is 1, right? Degree, or I could have put d for continuity. Degree is 1. It's the exponent that's on x. Remember, it's always an understood 1 if there's nothing there. And there's 2 terms here. Over here. This one is not a polynomial because it's a rational expression, right? It's a rational function. So no, we call this a rational function. So it's you have stuff divided by each other. So no, it's not going to be a polynomial, right? Polynomials are just the nice, neat looking functions. This one down here, now this one's actually pretty interesting. I've got all positive numbers on my exponents. So is it a polynomial? Yes. And the question is, how many terms are you going to have? Now, let's actually figure out what this is going to be. X minus 3 squared, so we have 5x times x minus 3 squared is x squared minus 6x plus 9, if you FOIL it out. So that's 5x cubed minus 30x squared plus 45x. So I've got 3 terms and a degree of 3. Degree is the highest exponent, so your degree is 3. Your terms are 3 as well. 5 to the x. Now this is interesting because x is up here in the exponent, so we're going to call this no. This is exponential. All right. Let's keep going here. Exponential just means there's a variable in the exponent, right? And that's a little bit of algebra 2 there for you. So number 9, it says determine the degree and roots of each polynomial and use your graphing calculator to help you sketch a graph. Okay, so we're going to introduce a couple of vocabulary words here for you. First off, this is x minus 2 and x plus 3. It's already factored for us. If you were to FOIL this thing out, you would end up with a degree of 2. So that's going to be like a parabola, right? And you have roots at x equals 2 and x equals negative 3. So that's going to cross the lines here, 1, 2, and 1, 2, 3. Just for the sake of time, I'm not going to use a calculator to help me out with this because I already know what's going on here. But this is called a single root. And you see how it only happens once? It's called a single root. That means that it crosses the x-axis. So single roots cross. Right? The next one over here, x times x minus 4 squared. So if you set each one of these to 0, you get x is 0. And then x minus 4 squared equals 0. So that's, that means there's 2 of these here, right? There's an x minus 4 and an x minus 4. If it's squared, that means there's 2 of them there. So you get x is 4 and x is 4. See how that happens twice right there? Alright, if you multiply this all out, we'll have x squared times x will be x cubed, so this is a degree of 3. And the roots happen at 0 and 1, 2, 3, 4. Now this 4 though is called a double root. Here's what this is going to look like. Since 0 is a single root, I'm going to cross here. And a double root means that you bounce off of the x-axis and come up again. And then just complete your graph. Again, this is called a double root. So double roots are where you hit the x-axis and you bounce back the same direction you just came from. So if it was down here, it would go bloop, boop, and come back down. Again, that's called a double root. So a single root hits and passes through. Double root hits and bounces back up. All right, negative x minus 2 to the third. Now that means that there's 3 of them here. If you set that to 0, it would be 2. And there's 3 of them there. So I've got a degree of 3 first off. And I know I'm dealing with a reflection because of that x. So here's what this is going to look like. I'm going to be opening down. And over here at 2, this is an idea of what a triple root is. All right, this is going to be what a triple root is. And if you notice, it actually changes concavity. I'm going to give you a calculus term in just a second here, but this actually changes concavity at this triple root. It goes from concave up, which is opening up, to concave down, opening down like this. So at a triple root, you change concavity. And then over here, we've got a negative sign, so we've got a reflection, right? First, my degree is x squared and x squared, so that's going to be a degree of 4. If you multiply x squared times x squared, and it looks like we've got another reflection here, so it's going to be opening down. All right, so my my zeros are going to be at 0 and 4. Set both of those to 0. But 1, 2, 3, 4. Special thing about these is they're double roots again. So it's 0, 0, and 4 and 4. So since I'm opening down, I'm going to come from below, hit it, bounce off, go up, hit 4, and bounce off. So I've got two doubles right here. Double root here, double root here. Double your pleasure, double your fun, double your delight with a rhyme. Sorry, sidetracked. Graph the polynomials. So the graphs of polynomials are smooth and continuous. These are both calculus terms, smooth and continuous. Smooth means there's no breaks, no gaps, no holes, and no sharp turns, no cusps, right? Remember, this is called a cusp. Your domain is all real numbers. The end behavior of the polynomial will be the same as the power function of the same degree. So that just means like x to the fourth right here. Degree was 4x to the fourth. Both ends go the same directions. A polynomial of degree n has at most n roots. That means that the most number of roots you can have is the same as your exponent. So if you have a third degree, you can have 3 roots. Fourth degree, 4 roots. Fifth degree, 5 roots. And you see how that could keep going. So let's talk about what a single root does. It causes f to change sign. That means it goes from positive to negative. We call that crossing the x-axis. At a double root, f does not change sign. Right? And this is what we call bouncing. Bouncing off the x-axis. It hits it, but it doesn't cross. And then a triple root, f changes signs and concavity. Now we call this a point of inflection. Not infection, but inflection. Your concavity changes at a point of inflection. All right, so keeping all of that in mind, what I'm going to do is come over to the back and just sketch a few more graphs, just using the information I know. So I've got 3 x's here, so I'm going to have a third degree polynomial. And I know I've got zeros at 0, 1, and negative 4. Notice how I don't have any repeats, right? So at 0, at 1, 1, 2, 3, and negative 4. Everything is positive here, and if you ever get confused, you can always multiply it out. But everything is positive, so my right end goes up. And I want you to write that down real quick. A positive leading coefficient tells right end behavior. So that means that my right end behavior is going up. If it was a negative leading coefficient, the right hand side would go down. And we'll see what that looks like in a minute. So these are all single roots, so I'm going to cross, cross, and cross. My degree is 3, so my 2 ends should go the opposite way. Remember, we talked about this being an odd function. It means that the 2 ends are going to go opposite directions, one up and one down. So since the right hand was going up, that means the left has to go back down. Okay? Number 14. Well, first we got to do some work to this. It's obviously a degree of 3. But I'm going to need to factor this to find my roots. X squared minus 4x plus 4. X, and we'll have I need to factor x squared minus 4x plus 4, which is x, negative 2, and negative 2. So it looks like I've got zeros at 0, 2, and 2. Got a double right here. Alright, so that means that at 0 it's going to cross, and at 2 it's going to bounce. The question is, what do you do? I look at the leading coefficient. Here it's a positive 1. That means the right side must go up. So I'm going to bounce and cross. It's a third degree, so you know the ends are going opposite ways. Right? Number 15, I'm just trying to get these knocked out here pretty quick. Your degree is 4. And it's negative, right? I'm going to be careful of that. So it's a reflection. Alright, so let's factor this thing out. This is going to be, take out negative x cubed, and you get x plus 3. Alright, so x equals 0 is going to be a triple root, because there's 3 of them there, and negative 3. Alright, so I'm going to look at what my right-hand side does. My right-hand side is going downwards. So I'm going to be opening down like this. My left-hand side here, my left-hand side is going up. Now, because this is a triple root, I also have to change concavity. So I'm going to go up like that. See how I'm concave down here, concave up here? But I still have to cross here, so I'm going to need to turn again. And that makes sense because it's a degree of 4 that both ends have to go the same direction. They got to go down. Down because it's negative. Alright, over here, a couple of things. It's a degree of 4. It's positive, so both ends are going to be pointing up. And then let's factor this thing out. I can take out x squared, and I'm left with x squared minus x minus 20, which is x squared, and I need to factor this, x, and that's, I need it to add to a negative 1 and multiply to a negative 20, so negative 5, positive 4. So I've got 2 roots at 0 from x squared. I've got a root at positive 5 and a root at negative 4. So it's going to bounce at 0, cross at negative 4, cross at 5. And since it's positive, both ends are going up. Now if you wanted to, you could do it like this and start by graphing both ends and then just fill in the in-between. You know it's going to have to cross here, you know it's going to have to cross here, and you know it's going to have to come up and bounce off of 0. Just like that. So it's a little bit of an art form, but with a little bit of practice, these things start to get much, much easier. The more you do them, the easier they'll get. Have a great one.